I want to start with this very simple problem. It is textbook problem. Minus y double prime equals lambda y. Y0 is 0. Y prime 1 equals a lambda y1. This is 0. This problem can be found, for example, in the book by Abramovich Levin, Equations of Mathematical Physics. There it appears in studies of torsional vibrations of a shaft at one end. You can also find that same book, that same problem in Tikhnov and Samarsky's textbook, Equations of Mathematical Physics. And there it appears in studies of the vibrations of a homogeneous string. This problem also appeared recently, problems related to viscosity of pneumatic liquids. You can find this problem in other physics context. So how do you solve this problem? It's not difficult. General equation of that differential equation is yx lambda equals c1 cosine square root of lambda x and plus c2 sine of square root of lambda x. Because of the first boundary condition y0 equals 0, that means that this c2 is 0, this part disappears. Since c1 should be different from 0, lambda is not 0, we obtain from the second boundary condition that cotangent square root of lambda is x. This is a transcendental equation. If you replace square root of lambda by mu, the solutions will be intersections of this cotangent function and this line function. These are the eigenvalues. These intersections correspond to eigenvalues. You can find the eigenvalues using tables of special functions. For example, in our case, we can use this column x tangent x special functions. Find those eigenvalues. Of course, nowadays, who does this with tables? Algorithms, computer programs do this instead of tables. These eigenvalues can be determined. Let us now look at a more general problem, the main focus of today's talk. The first equation is a little bit different from that textbook example. There is a qxy part. First boundary condition is also more general. The third condition, which makes it new, is this. There is a spectral parameter in quadratic form in the boundary condition. We also consider the case when a is 0. The papers of Binding, Browne, Watson, and Code, there are several papers. The existence and asymptotics of eigenvalues were studied. It was proved that the eigenvalues form an infinite sequence, accumulating only at plus infinity. And the following cases are possible. All the eigenvalues are real and simple. All the eigenvalues are simple, and all except a conjugate pair of non-real are real. All the eigenvalues are real, and all except one double are simple, and all the eigenvalues are real, and all except one triple are simple. So either all real simple, one pair of complex eigenvalues, or one double eigenvalue, or one triple eigenvalue. These are the all possible cases for this problem. This word is proved in the papers that I indicated here. The same authors also found asymptotic formula for the eigenvalues. So for the affine case, asymptotic formula looks like this, depending on beta, angle beta. It can be like this or like this. There are more terms actually available from their accuracy. These quadratic terms are enough for us. In the quadratic case, the formula of the eigenvalues is like this. Forward, okay. So we are interested with the basis properties in LP01 of the root function system. The root functions, we mean eigenfunctions and fixes associated eigenfunctions. We call them associated functions. This topic was studied in many papers before. Professor Chirimov's paper with Mirzoev in Siberian Metro. Before that, myself and Kapustin in applied mathematics. There are also papers from the previous period by Rusakovsky. I have to also mention the paper by Shkalikov and his recent paper in differential equations from 2019. We return to this topic again and studied similar problems. So our approach is to work with characteristic function. So we assume that yx lambda is the non-zero solution of the differential equation satisfying the first boundary condition, and we use the second boundary condition to write this characteristic equation. Of course, if this omega lambda is equal to 0, then second boundary condition is also satisfied. This numbers we will call eigenvalues. We say eigenvalue is a simple eigenvalue if the derivative of the characteristic function is not 0. If first derivative is 0 but second derivative is not 0, we call this double eigenvalue. If in contrast second derivative is also 0 but third derivative is not 0, then we call this triple eigenvalue. Also, we will frequently use the fact that if normalize it properly, then yx lambda, which you remember was the solution of differential equation and this first boundary condition, then yx lambda approaches yx lambda n, which is yn. N is eigenfunction, if, of course, is properly uniformed. And as usual, we denote by this scalar product in LP01, and by this we denote norm in LP01. We can find inner product of eigenfunctions easily. With some efforts, we can also find inner product of eigenfunction with itself using this derivative of the characteristic function. The case when lambda n is a double eigenvalue, then this disappears. This eigenvalue is double if omega prime lambda n is 0. So if this is 0, then we apply this formula for. And we can also find product of eigenfunctions in complex cases when lambda r and lambda s are conjugate of non-real eigenvalues. Then their inner product and norms look like this. If it is visible, the below part of the slide. Okay, but this is not enough. We also need to know something about associated functions. Associated functions we define following the steps of Neymark's textbook. Differential apparatus. The associated functions are defined like this. First boundary condition is not different from the boundary condition of the original value problem. First, the second boundary condition is defined like this. It can be explained why associated functions should be defined exactly like this. I will return to this in a few seconds. But it is important to note that eigen-associated functions are not unique. So if you have an associated function, you add to this associated function a multiple of eigenfunction, you get again an associated function. There are many associated functions. Why the conditions of the associated function were like this? You can easily understand it from this. So we took the first differential equation, took the derivative with respect to lambda. So the first boundary condition and the characteristic equation. And when you look at these derivatives of the original equation, you can easily see the trace of this condition for the conditions for first association. So we take the original equations and take derivative with respect to lambda. And this tells us why the associated functions are defined like this. Also important to note that the derivative of original function yx lambda with respect to lambda, when lambda approaches to that double eigenvalue, approaches to a very specific associated function, which we denote with this tilde symbol. So it is a very special associated function, first associated function. It will play crucial role in our future slides. We assume that with the chosen associated function yx plus 1, their difference is multiple of yk, where c is also a fixed. So we can also find this c. We can do the same with second associated function, which is the last one for this problem. If lambda k is a triple eigenvalue, you can define second associated function using again the Nymax definitions. And again, second associated function is not unique, because if you add to second associated function a multiple of eigenfunction, you get another second associated function. Also, it is important to note that when you change the first associated function with something else, with a new associated function, automatically your second associated function also changes. Again, this explains why these definitions of second associated functions look like this. We just took the derivative of the original three equations with respect to lambda, but twice. Again, when you tend lambda to that triple eigenvalue, y lambda approaches a very specific second associated function, which will again be very useful. Theorems. Okay, after these definitions, we can now define defined associated functions with eigenfunctions, including its own eigenfunction, yk, and with itself, yk plus 1 in a product, yk plus 1. As you can see from this, we have a tail-like part in this inner products. We have, of course, a familiar part, but also this tail, which can be or cannot be zero, depending on the chosen associated function. Similarly, for the second associated function, you can find their product with other eigenfunctions with its own associated eigenfunction, the first associated function with itself. All of this formula feature derivatives of characteristic function. This yk plus 2 with hat and yk plus 1 with hat. These are other some specific associated functions, well defined. Now, one can ask this natural question, are there functions yk plus 1 and yk plus 2 such that there is no tail part like this? There is a simple formula for the associated function, same for yk plus 1. Formula, an associated function for which there is no tail like this. It's purely mathematical question, but later we will see that these functions play a crucial role. Yes, there are such functions. There is a function yk plus 1 star, very special associated function, such that This inner product is defined in a very simple, no tail part. Same for yk plus 1 ds. Whose inner product with yk plus 2, yk plus 1 don't have that tail part. Now we are ready, after defining these special functions, associated functions. Now we are ready to discuss minimality results. After these minimality results can be converted to basis properties. Now, this phenomenon of redundancy in the system of eigenfunctions, associated functions, was a well-known fact. It is known for very long that if you have spectral parameter boundary conditions, then one of the functions is redundant. So to get a basis, you need to throw one of the functions from the system. So the remaining functions will form a basis. This is a well-known phenomenon. First works about this appeared in papers by Shkalkov and Kosakovsky. And another paper by myself inspired us to study this type of systems. But it is interesting that sometimes when associated functions are in the system, you need to be careful with what you throw out of the system. So in some cases which are shown here with a different color, if you, for example, leave the associated function in the system, but throw the eigenfunction corresponding to that associated function, it is possible that the system will not be minimal. Automatically, if it is not minimal, it is not a basis. How do I know if it is safe to keep this yk plus 1, this associated function in the system or not? Those functions that we defined before this theorem will be very handy here. Everything depends on the value of those special associated functions at the point 1. There are similar, these results are for affine case, no quadratic dependence on the spectral parameter. Similarly, imagine you triple eigenvalue case, you have eigenfunction, it is associated function, and it is second associated function. Imagine you delete from the system first associated function, but keep the second associated function. It's not always a minimal system. There are some conditions in the system which will make it minimal. Similarly, imagine you keep first associated function and second associated function, but delete the eigenfunction from the system. Again, it is not always basis. These results were published in 2007. Recently, I returned to this topic again in 2021. Now, these conditions that we saw in the previous theorem can be replaced by some simpler conditions using only characteristic functions. So, for example, this condition can be written like this. Just check, I will show you in the example. This condition for the first associated function can be written like this. Little harder one is this. This function, this number is different from 0 when d is different from this expression, complicated expression. And these results were used also by my former supervisor Kerimov and his students in Mersin University. Now we can start quadratic keys. Now for quadratic keys, there are of course more options. This time you need to throw two functions from the system, get a minimal system. But if you throw two functions, there are many possibilities. For example, in the double eigenvalue case, you have an eigenfunction and it is first associated function. There is no second associated. You can delete both of them. Yes, eigenfunction and it is associated function. You can keep one of them, isn't it? Or you can keep both of them. Delete completely other eigenfunction, not corresponding to double eigenvalue. So there are many possibilities here. In some cases, like here in this case, when you throw the eigenfunction corresponding to double eigenvalue and another eigenfunction, but keep the first associated function. It is not always a minimal system. There are some conditions over this. Similarly, in the double eigenvalue case, you have eigenfunction, it is associated function and second associated function. Then, for example, you delete eigenfunction and second associated function and keep the first associated function. It is not always minimal. There are some conditions over here. Or you delete eigenfunction and this first associated function, but keep the second associated function. Not always minimal. There are some conditions. More cases, imagine you keep eigenfunction and it is second associated function, but keep the first associated function. Not always minimal. Or you eliminate from the system eigenfunction, but keep the first and second associated functions. Not always minimal. There are some conditions, necessary and sufficient conditions for minimal. Of course, there are also cases when it doesn't matter which functions you keep in the system. It is always. This result was published in 2008, the Arabian Journal for Science and Engineering. Recently, we returned to this question and we tried to write these conditions that you saw here in a simpler form. So we did this for affine case. I mentioned this. In affine case, these conditions can be replaced by conditions involving only characteristic functions. But back in 2008, we couldn't do this for quadratic case. And recently, we returned to this question and found those conditions. For example, this condition in the case of double eigenvalue can be replaced by this simple condition, which can be easily calculated, which we will see in the examples. Similarly, this condition can be replaced. This condition can be replaced by this. These are not elementary results. This took much time and efforts to simplify these conditions into this. For more conditions, this condition can be replaced. This, and the hardest one probably was this. This condition, after less simplifications, replaced by this condition, which on examples can be easily verified. I have some examples. If you are not tired, I can show some of them. So look at this boundary value problem, minus y double prime equals lambda y, where x is between 0 and 1. First boundary condition is simple. Second boundary conditions contains lambda quadratically. Calculate yx lambda, which is the solution of this two, of this derivative with respect to lambda, and the characteristic equation, which is taken from here. Can be seen here. This example was also discussed by Maris and Göktaş. Here you see the graph of characteristic equation. You see the intersections. These are our eigenvalues. By the way, this same example was also discussed in these papers by you. Interested in numerical problems about this. So he used these examples to study numerical. So one of the eigenvalues, more precise, the eigenvalue equal to 0 is a double eigenvalue. The next eigenvalue, p squared, is a simple eigenvalue. All the other eigenvalues are simple. They are the solutions of this transcendental equation. You can write first eigenfunctions, y0, y2, and the others. Now, if we will calculate the first associated function, special one, when you take the derivative of y with respect to lambda and approach lambda to that double eigenvalue, it's minus x squared. But the others, other associated functions are minus x squared plus c. We can calculate easily that c is minus c tilde. C tilde was defined using a special associated function. And after some calculations, we obtain also this special associated function, which will play important role in our condition for minimality. And we check the minimality condition using first form of the condition. We obtain that C should be different from this number to make this system a basis, a minimal system for L201. So if C is equal to this, then this is not a minimal system. What happens if C equals to this? Then we have a function which is orthogonal to all the elements of the system, which means that it is not complete, and therefore it cannot be a basis, and therefore it cannot also be, and also it cannot be minimal. You can also check this with the other method. Do you remember? We said that we can replace this condition using with this. And when we check this version of the minimality condition, we get the same result. So both give the same result. I have more examples, but maybe I can stop here. I have more examples to show. Some of them appeared earlier, and I repeat these examples again. So there is another one where we have, again, double eigenvalue. Double eigenvalue can be seen here. I squared over 4 is a double eigenvalue. Check it, those same conditions here. And I got the same result using the earlier version of the minimality condition and using the new version of the minimality condition. There is an example about triple eigenvalue. Here, 0, lambda equals 0 is a triple eigenvalue. This example attracted attention of another mathematician, Troitsky. He is from Ukraine. He lives in Kharkov city, which was media recently. You probably know this Ukraine. Troitsky, I contacted him. He was that time was in Kharkiv. He was interested in this example. He applied numerical methods to calculate the eigenvalues of this boundary value problem. So again, you see the graph of characteristic function. You see that lambda equals 0 is a triple eigenvalue because of the shape of this tangent x-axis of second order. Again, one can try to use for minimality conditions earlier version using the specially defined associated functions. One can also use new version of conditions which give the same result. Okay, I think I can stop here. Thank you for your attention. This was all from my part.